It's a little bit strange that we're gonna prove the quotient rule first. That's not strange. Before we prove the product rule, we haven't done that yet. But we're going to prove the quotient rule using the product rule, and we haven't proven the product rule. Maybe that's not strange to you. That's a little bit strange to me, because whenever we're proving something based on something we haven't proven, it's a little bit sketchy. But as long as we have time at the end of the lesson today, we're going to prove the product rule. For now, you'll have to just take my word for it that the product rule is correct. We did demonstrate that it works with a bunch of different kinds of functions, so it's pretty believable. But anyway, we're going to prove the quotient rule just because it's a bit of a simpler proof. It's very different. We're not proving it from the definition of a derivative. We're proving it just using the product rule. Okay? So what you do is you take, so again, the quotient rule, I mean, we haven't even talked about it yet, but it's when you have the quotient of two functions. So f at x is p at x divided by q at x. So what we're going to do is we're going to take this and turn it into a product by moving q at x over. Then we'll use the product rule to take the derivative, which is for those of you who weren't here yesterday, here's your quick lesson on what the product rule is. The derivative of the first thing times the second thing plus the derivative of the second thing times the first thing. And I will say this, this was another problem with the learning goal that mistake that people made was the learning goal from yesterday was a quotient of two things, and people just did the derivative of the top over the derivative of the bottom, and that is not what the quotient rule is. Just like yesterday, people would think, I'm going to write this down again, you probably shouldn't write it down because the danger of you thinking that it's true. If f at x is, actually I'm going to do it really sloppy here, is p times q. If f is p times q, then people think the derivative of f is just the derivative of p times the derivative of q. And this is not true. It's not correct. I think most people know that it's not true. I think the bigger mistake is people don't realize they're looking at the product of two things. They don't realize this is a product rule question once we get deeper into all of this. And you get something like if f is x times x to the fourth or something like that, which could easily be simplified, but people don't realize it's the product and they just take the derivative of each part individually. Okay, but that would be wrong, right, in this case. So be careful of that. It's exactly the same for, you just got to remember it's more complicated when you're taking the derivative of a product or a quotient, and you really just have to, I guess, practice enough that you recognize when something is the product. We'll talk a bit more about that today. Actually, there's some really nice examples that will highlight that, but you really just gotta get to a point where you recognize what you're looking at. Okay, and again, it's just a matter of practice. There's really no rule about it. It's a bit of an art, and it just takes some time to get there. And as I said, the same is true for quotients. You can never just take the derivative of the top over the derivative of the bottom. Like, that's just not a thing. Okay, and we'll see what the actual rule is momentarily. So what we actually started out here wanting to know was what's the derivative of f, because that was the thing that was a quotient. So all we have to do is take this thing and isolate f and sort of replace a couple of things, isolate f prime, replace a couple of things to put it in a form that we can use. So I am going to sort of flip sides here, f prime at x times q at x equals p prime minus q prime times f. So I sort of flipped sides, but I also moved this to the other side, subtracted it, because I'm working towards isolating for f prime, because then we'll have something that is the derivative of f. That's what we That's what we wanted. That's what we were starting with. We want everything to be in it doesn't have to. Not everything in mathematics works this way, but in this case it will. We want it to be in terms of P and Q. So I'm going to replace f at x with P at x over Q at x. That's just what we let f be originally. Then I'm going to get a common denominator of Q at x. So this is going to be P prime times Q over Q minus Q prime times P over Q. Of course, we could have actually put those together in the same step, but just for clarity, I'm writing it out twice. Okay, so common denominator. And actually, we're almost done. So this one is simpler because it's based off of a rule we already have. Now I'm just going to divide both sides by Q. And what that's going to do is give me Q at x on the bottom all squared. And that's it. That's our formula. That's our rule. The derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. So I am going to rewrite this. All right, so now let's use the quotient rule to take some derivatives. Whenever we learn a new skill, we always think the skill in and of itself is like, that's what math is or something, I don't know. But really, derivatives allow us to do something. So they allow us to find properties of functions, solve problems, that kind of thing. Eventually, what calculus is about is using the process of derivatives as a tool to solve other problems, right? To do other things. That's where all of this is going. We saw that a little bit when we did problem solving, finding equations of lines, that kind of thing. But there's way more to it, obviously. So we're in this unit, we're getting caught up with just differentiating. But don't forget that down the road, we're actually going to be just using derivatives to do things. This is a very simple example. So I'm just going to go ahead and take the derivative. So it is, and I'm going to write this, f prime is the derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared. When f, this is like the lazy way of writing it, is p over q, right? But just as a reminder that that's what it is. So what is the derivative of the top? It's 5 times the bottom minus the derivative of the bottom, which is negative 2 times the top all over the bottom squared. And this is an example where it's going to tidy up really nicely, but like, I think you can look at this and you can see that it will, because all I have is a constant times a binomial. Like, there's nothing all that complex. There's no big exponents or anything happening here. So it is something that you could look at this and be like, oh yeah, this is going to like kind of simplify nicely. But don't get caught up on how did you know to simplify that one and not that one right now. Like, don't worry too much about that right now. So this ends up being 45 minus 10x plus 10x plus 14. Again, this is why I was saying, like, down the road when we're using derivatives for things, it will be obvious that you have to clean it up for what it's being used for. But it's fairly reasonable at this point with the abilities that we have that you could look at that and realize, you know, in 1 or 2 steps, it's going to kind of come together nicely. We compare that to some of the other questions we're going to look at that you're like, yeah, that one, no, I'm not going to touch that one. So this is one I was alluding to. This is one of the questions, one of the examples we're going to look at today that I was alluding to earlier, where you might not notice that the bottom is a product. And this is the thing, like, if you didn't notice that and you tried to take the derivative, I don't know what you would do. You'd be making up your own rules. How do you take the derivative of this? With the product rule. It's the only way to do it. It's the way you have to do it, right? But people think, oh, this is a quotient rule question, so I'll use the quotient rule. But the quotient rule is the derivative of the top times the bottom minus the derivative of the bottom. Well, what's the derivative of the bottom? You would have to use the product rule because it's a product. And people miss it, and they don't, and they just make some up some other way. They just take the derivative of each part individually, and then you've made a mistake. Okay. For this question, I'm actually not going to, I'm going to expand. So again, this is where you have to decide how you want to do it. You could use the product rule on the bottom. I think it's easier to take a step and expand. And I can only imagine, again, that some people are like, well, how do you know when to take a step and simplify, or when to use the product rule, the quotient rule, or whatever it is? But I can't give you a totally straightforward answer to that question. There's no rule about when you do, when you don't. It's a matter of preference, and it's a matter of, you know, getting used to it about what's easier. You can tell for a question like this is the easier way, right? But what I'm trying to say is you can't leave it like that and take the derivative without using the product rule. Okay. So now it's the derivative of the top, which is 2t minus 4 times the bottom minus the derivative of the bottom, which is 7 minus 2t times the top all over the bottom squared. Having all the brackets in the right place, watching all the exponents, everything like that is all just necessary. It's all part of it. It's all tricky, obviously. You got to be really careful. This goes all the way back to grade 9 when we started doing some serious algebra. And like, it's really hard in grade 9 for some reason. Even just collecting like terms and multiplying. The difference between x plus x and x times x is something that, like, you know, half the class in grade 9 doesn't get. But all that little stuff, all those skills that we've been picky about from the beginning, they all, you know, come together here because you can't not have brackets around things that need brackets. It's crucial, right? You can see that. And this is one that I'm not going to clean up. I'm not going to expand because I've got, like, this is only a product of 2 binomials, but, you know, they don't have the same exponents. It's not going to clean up nicely. And then this is a trinomial, and it's all over the place. So it's not going to help. It's not going to. Again, it comes down to instructions for questions, that kind of thing. But in this case, there just doesn't seem to be a point in cleaning it up. If you were doing something with that, you might have to. But we're not going to worry about that right now. This is another example where the top is a product. So if I didn't do anything to this, and I tried to take the derivative as is, the quotient rule says the derivative of the top times the bottom. So the derivative of the top is a product. I would have to use product rule. And there are times where that will happen, where you can't simplify first. And in the process of using the quotient rule, you'll use the product rule or some other rule. That will happen. But this isn't one of those cases. It's easier to expand before taking the derivative. Okay? Now you can go ahead and try this one if you want. I mentioned this before. There's no reason why I change and use different notations just to get us. It's just a matter of getting familiar with the different kinds of notations, that y prime is the same as dy by dx. They're not different. Okay? And there's one case where you're told to use a particular kind of notation. I think we'll talk about that on Friday, so don't worry about it right now. It's called Leibniz. This one, it's called Leibniz notation. And there is a time where it's just easier. It's a really useful notation for a certain kind of question, but we'll talk about that later. So right now I just flip back and forth just to sort of get us used to using all the different kinds. There's no reason why. So derivative of the top times the bottom minus derivative of the bottom, which is just 2x times the top all over the bottom squared. Good? Any questions? All right, now let's take a look at an example of us using this. In the Block A class, I didn't notice that there was a number missing. If you were in my class before, sometimes when I create these worksheets, it just randomly chooses one character not to print. It's so bizarre. And so for some reason, when I made this, instead of 16, it just came out as a 1. And the answer when we got to the bottom was like a disaster. I'll show you after, but like it was a mess. And I kind of got to the bottom and I'm like, what kind of an answer is this? And realized that there was this mistake. But so anyway, but then I noticed. So now you get the actual question. Whereas the Block A class got a really kind of messy ending to this problem. So this is one of those 3 kinds of problem solvings that we did a couple of days ago, where you're finding the point. Remember, the different ones are find the slope, that's the easy one. Find the point, and then the third one is find the equation. What does it mean when it says the tangent line is horizontal? For starters? Yeah, so we have to, the first connection we need to make here is that this is saying slope is 0. Right? So it's giving us the slope. We find the point. Sometimes it gives us the point or gives us the x value. We find the slope. And then the last one is find the equation of the line. Usually you're given a point or the x value for that one. Okay, so we're going to start by taking the derivative, and I think we are set to take the derivative as is. We don't have to clean it up or anything. Now, the derivative of the top is just 1. So that was easy. So it's 1 times the bottom minus the derivative of the bottom, which is 3x squared times the top, which is x, all over the bottom squared. And again, here's a case where like, yeah, we need to clean this up. Well, yeah, we're going to have to anyway. So whether you did it now or did it later, you're going to anyway. But if you look carefully, the top is going to simplify kind of nicely. It's not hard. It's not a lot of work. So it's worth it. And I believe it works out to negative 2x cubed minus 16 all over x cubed minus 16 squared. Now we're finding the points where the tangent line is horizontal, so I'm just making a note. You wouldn't have to write this, but for horizontal tangent, we're going to take that expression and set it equal to 0. And this is something that we do like a lot of. Okay, so you're going to get very used to it, but if you were, in some cases, like we often set it equal to 0. This is a heads up of what's coming in the rest of this course. We set a lot of things equal to 0. But in a question like this, it could have said when the slope is equal to 2 or something like that, right? It could have given us any slope. It happened to say horizontal for this question. From MHF, how do I solve this? This whole thing is equal to 0 when? Very nice, when the top equals 0, right? We don't care about the bottom in this case. You could think of it as multiplying through by the bottom. Quick reminder that solving rational inequalities is a lot harder than solving rational equations. We do a lot more equations, so that's good. And really, all I care about is the top when I'm trying to solve this equal to 0. So I'm going to move 16 to the other side. Divide both sides by 2. And take the cube root. So it works out to negative 2. So this was where the other class things got hard, and I was like, this doesn't seem right, because we had a 1 there. So this ended up being negative 1/2, and it was negative the cube root of 1/2. And we're not done yet because we have to find the point. So we had to take that and sub it into the equation and solve for y. And it was like, this. There's no way that this is right. And it's because the silly program didn't print the 6. But anyway, so we're good. So like I said, the question says find the points. So there's only one in this case, but so we've got the x value, but since it's a point, we need to find the y value as well. That's a mistake that people make just because they're rushing on tests, that kind of thing. So be careful of that. Always go back and reread the question and make sure you've finished it before you actually move on to the next question, I guess. So at x equals negative 2, y is negative 2 over negative 2 cubed minus 16. And some people might take this and sub it into the wrong formula. So that comes down to the derivative represents the slope of the tangent of the original curve. But if I'm trying to find a point on the original curve, I got to sub back into that equation, right? We end up with more than one equation, and so that causes people problems. So this works out to negative 8 minus 16, which is negative 24, which is 1 over 12. Therefore, the point is, when the tangent line is horizontal, is -2 and 1/12. Any questions about that? I think we have one more to do. Yeah. So the first one gave us the slope, said find the point. This one's giving us point, the x value of the point at least, and asking us to find the slope. And this last one, again, is a really great example of how you got to make choices when you're starting these questions. I'm going to tidy up the top. I'm going to simplify on top. Because I think this is going to be easier to take the derivative of than that product. Again, that's a product. I could expand the bottom. It wouldn't be too bad. If that's your preference, by all means, go for it. I'm going to leave it because I think it's a good reminder of how these questions can have these little details that we have to watch out for. When I take the derivative of the bottom, that's power of a function. We did this yesterday for those of you who weren't here. Hopefully you looked at it. So this is a function t squared minus 4 raised to an exponent. Different from like if it was just t squared, right? This is just a monomial. We know how to take the derivative of that. Yesterday we learned how to take the derivative of something more complex by this, called power of a function is what we call that. So when I take that derivative, I got to use that rule. So while we're using one rule, we end up using other rules as well. So it's just like there's so many layers, there's so many steps, so many places that you can make a mistake, and that's just the unfortunate nature of all of this. So derivative of the top, 48t to the 5 minus 24 times 5 is 120 t to the 4. Times the bottom minus the derivative of the bottom. So if you want to watch, this is where I'm using the power of a function rule. So we multiply by the exponent, and then we have the function. Decrease the exponent by 1, subtract 1 from the exponent, so the 2 becomes a 1. And then multiply by the derivative of what's inside of the actual function that we had a power of. So then I also have times 2t. And all of that times the top. Whoops. And all of that over the bottom squared. Which means it's t squared minus 4 to the 4th power. And that's a common thing that you have. We saw that yesterday when we took, when we were doing products and also had powers, but I'm doing the quotient and I have a power, or maybe you have a product inside a quotient like this. Just, you know, this is why we need to be really good at all of this. In this case, I am not going to clean this up. It would be kind of a disaster. I mean, that's binomial squared times something with big exponents. I'm going to clean this part up a little bit, I think, but I don't even know if you would bother taking a step to do that, actually, because same thing. It's not going to tidy up nicely, and we're just subbing in 1, right? It said find the slope of the tangent when t equals 1. So I'm actually just going to go at t equals 1, and I'm going to sub in s prime equals 48 times 1 to the 5 minus 120. 1 squared minus 4 is negative 3 squared is 9. This is 2 times negative 3 times 2 again. So I think that's 12, right? So minus plus 12, because it's negative 2 and this is negative 3. So I think that should be plus 12 times 8 minus 24. And then this is negative 3 to the 4th, so that is positive 81. I think that works out like that. Any questions?